Okay, so let me start so we can only recall. So finally we got the following result. If omega is any uncountable set and let mu be the counting measure, and if we have a function from omega to c, let us denote by SF the support of f, that is the set of all points omega is not equal to 0. Then we found that f belongs to L2 omega mu if and only if SF is either finite or countably infinite. And integral f d mu, which in that case becomes the integral over the support of f, which is by definition of the integral is over omega s. Mod f omega squared is finite. Okay, it consists of all such points. How do you define?
No, why is it? It's not if and only if, right? Because
We can also show if and only if.
it is supported on a countable
Set. And if that sum is finite, that is the integral. Okay, we are going to look at L2. So we want that integral to be finite. Okay, it has to be. In that means that integral should be finite. But that integral is precisely that. Okay. Yes, that's a good question. I saw only this way, but the other way is obvious. Okay. So analogously, for 1 less than or equal to p less than infinity, we can see that Lp omega mu is the set of all functions from omega to c such that the support of f, as before, the cardinality is less than or equal to alpha, either finite or countably infinite, and integral omega to mod f p to the power of d mu, which by definition of integral will become omega belonging to SF of mod f omega to the power of p. That is finite. Okay. That will be the corresponding version for LP spaces, and just like in the other cases of all these LP spaces, only p equal to 2 is the inner product space. Okay. Only okay, in these spaces norm Fp is defined to be as usual integral over omega mod Fp to d mu to the power of 1 over p, which by definition is summation omega belonging to the support mod f omega to the power of p to the power of 1 over 2. Okay. And all these become therefore norm linear spaces. So of these norm linear spaces, only p equal to 2 gives an inner product space, with inner product defined as usual integral f. Okay, first of all, inner product of f and g is integral. Now we have to look at f multiplied by g d mu. So we must have both f and g non-vanishing. So the points omega should not only be in the support of f, they must also be in the support of g. So the integral will be only integral over support of f and g, which is the same as take all the omegas which belong to both the supports and look at f omega g omega bar. Okay, and that is a regular sum, because that can be either finite or a sequence. So it is a normal sum, infinite sum or an ordinary sum. It is not a uncountable sum or anything like that. Okay. So this example is what completes the situation. We will see later that all Hilbert spaces can be modeled either as our n-dimensional L2n or our infinite sequence L2, or this, all of them belong to L2 omega counting measure. Omega finite gives us our L2n, omega countably infinite gives us our little L2, and omega equal to an uncountable set gives us the other possible Hilbert spaces. So all Hilbert spaces eventually will be shown to be isomorphic to these things. So you have to only work with these function spaces with the counting measure. So the counting measure plays a crucial role in the study of Hilbert spaces. Okay. You may look at L2 over the real line with the Lebesgue measure, but that can be converted to an isomorphic space where it is L2 over omega, which is a countably infinite set, and the counting measure. So you can bring it back to this space. That measure space can be brought back to this space. Okay, we will look at these things as we go along and see what Hilbert spaces are made of. So to that end, the crucial thing in Hilbert spaces is the inner product, which gives us the geometry. Inner product spaces, the main thing is the geometry, and the geometry is the orthogonal geometry. So we will next look at orthogonality. This will run parallel to what we did in linear algebra for a while, and then because of the infinite situation that may arise, we will have to do some extra things. Okay. So this is the topic I will start today, orthogonality. Orthogonality in inner product spaces. Okay. So suppose I have an inner product space then xy belonging to that space are said to be orthogonal if the inner product is 0. The inner product between the two vectors is 0. It is the generalization of the fact if the dot product is 0, two vectors are orthogonal in the usual n-dimensional space. Well, in fact, we can even do a little bit better in the sense that we can define the angle between x and y to be cosine inverse the inner product of xy divided by, if it is real, in the real case, xy by the length of x into length of y. Well, this simple formula is the starting point of the application of SVD to the latent semantic index ranking that we do. Okay, that is usually done. They are called LSI. LSI. The first thing is look at the angle between two vectors and assume that, and look at if you have a fixed vector which is a query vector, and then if you have various documents, and then the farther the document moves from the query, the more less relevant it becomes. So you start picking up the documents which make theta less angle, and that picks up all the relevant documents. One of the simple search methods, okay, which is called the LSI. I will not get into that. Okay, but the idea that the inner product spaces give the angle in the real case, and the general case it gives us the orthogonality. I wanted real because otherwise this will be complex, and I don't know what is meant by cos inverse, and that will create more complex problems. Okay, that is just by the way. So we have two vectors are said to be orthogonal if their inner product is 0. So I will make one or two simple remarks, very innocuous looking remarks, but very useful remarks. The one is, if you take this vector to be 0, then x comma 0 is 0. So the 0 vector is orthogonal to all the vectors, okay, clearly. Theta x is orthogonal to all vectors in the space. The second is, suppose a vector is orthogonal to all the vectors. Is this the only vector which is orthogonal to all the vectors? Let us see. If somebody else is orthogonal to all the vectors, he is in particular orthogonal to himself, and therefore x comma x is 0, and therefore x must be 0. So if so, x orthogonal to all vectors implies x comma y equal to 0 for every y in x. That implies in particular x comma x equal to 0. Since this is true for all y, I can take y to be equal to x, but we know the inner product property that x comma x is 0 only when x equal to theta x. So there are two things that we observe in this. One is the inner product says that if a vector is orthogonal to itself, then it must be the 0 vector, and 1 and 2 together give me that the only vector which is orthogonal to everybody is the 0 vector, and the only vector which is orthogonal to itself is the 0 vector. So the 0 vector has two special properties. Theta x is the only vector orthogonal to all vectors, and theta x is the only vector orthogonal to itself. By this definition of orthogonality, the definition of orthogonality is that the inner product must be 0. In fact, in many of the proofs, in order to show that something is the 0 vector, we will be doing this. We will be showing that it is orthogonal to all the vectors, and therefore it must be the 0 vector. A very complicated way of saying something is 0. Okay? So many times this criteria is used to conclude that something is the 0 vector. Okay, so these are three innocuous looking remarks which I will keep, and the next observation is just the Pythagoras theorem in the general. If you have, for example, two vectors which are orthogonal to each other, then this is the diagonal, then the diagonal squared is equal to the sum of the side squared. That is what the Pythagoras theorem says in a right angle triangle. So the diagonal is the vector x plus y. So norm of x plus y squared is norm x squared plus norm y squared, and that is true in the general case. Okay? X y orthogonal implies norm of x plus y squared is x plus y comma x plus y. The norm squared is the inner product of the vector with itself. Okay, so it is x plus y comma x plus y. Now the inner product is distributive, so we can take term by term products. X comma x, that will give me norm x squared, x comma y, then plus y comma x plus y comma y, which is norm y squared. Now since x is perpendicular to y, x comma y and y comma x are 0. The inner products are 0. So that says norm of x plus y squared is equal to norm of x squared plus norm of y squared since x y orthogonal, and hence x comma y equal to 0 equal to y comma x. So that is the Pythagoras theorem. If you have two orthogonal vectors, the diagonal square is equal to the hypotenuse square is equal to the sum of the two sides. Okay. So we saw the parallelogram law, and we are now seeing the Pythagoras theorem. We will also see a more general Pythagoras theorem later. More generalization of this Pythagoras theorem. So these are four simple properties of orthogonal vectors. Now we move to the crucial point, namely the important thing in this is all orthonormal basis. Whenever you have dot product, you have the notion of orthogonality, and we look for bases which form an orthonormal set. So the next important notion is that of orthonormal sets, and we will go through this slowly, step by step. So again I have a inner product space. We will first do some theory and then take up a few examples later. Okay. It's an inner product space, and then first suppose S. Okay, let me give the definition. And okay, a subset S of X is said to be the same definition, orthonormal, if one, that is if we take any two vectors in S which are distinct, if we take two distinct vectors in S, they must be orthogonal to each other, and any vector must have length 1. Okay. So then we say the ortho. The ortho part here is this, they are orthogonal to each other. The normal part is this, they have been normalized to have length 1. Okay. So the orthonormal has two information in it, the vectors are orthogonal to each other, and every vector is normalized to have length 1. So that is what is called an orthonormal set. Note, in general it may happen we may have a finite orthonormal set or an infinite sequence of orthonormal set that is countable or uncountable orthonormal sets. So we may have many situations like that. Probably I will give you an example of these things. Okay. So Hilbert spaces where we have only finite orthonormal sets and only finite orthonormal bases will be the ones that come from L2 n. The fellows like this will come with L2. The fellows like this will be the L2 omega which we saw just now. Okay. Okay, let's dispose of one trivial example for this. Okay. So examples. One, let us look at our inner product space to be this, n component vectors, complex, and the inner product, the usual L2 inner product. Then if we take for example S is equal to E1, E2, where E1 is 1 0 0 0, E2 is 0 1 0 0 0, then that forms an orthonormal set. I am not saying orthonormal basis, I am only saying orthonormal set. Okay. So the two vectors are orthogonal to each other and their length is 1. We can take E1, E2, E3 also, and in general E1, E2, Ek, k less than or equal to n. Okay. So this is, and S is equal to E1, E2, Ek, k less than or equal to n is an orthonormal set. Second, this is the case where we have a finite, we have given an example of a finite orthonormal set. Now let us take L2. What is L2 of C? It is all sequences such that the sum of the squares of the component is finite. Then if we take all such sequences, then let Ej be the vector which has 1 in the jth place and zeros elsewhere, and then Ej, j equal to 1 to infinity, is an orthonormal set in this space. Now we have a countable sequence, infinite sequence of orthonormal set. The set is infinite but countably infinite. So that is the second situation, finite or infinite. Now we look at, suppose we take L2 omega mu where omega is uncountable set and mu is counting measure, just the example that we saw just now. Okay. What does this mean? This means I have a set omega which is uncountably infinite. I am looking at all functions which take this to C, that is for every point a complex number is attached, such that only at a countable number of places it will be not 0 and the sum squared is finite. That is what this space means, what we define. Now what I do is I am going to define for take a point omega, corresponding to that I am going to define a function, define for every omega in omega a function f omega, f sub omega as f sub omega equal to 0 if x not equal to omega, 1 if x equal to omega. In other words, the function lights up only at that point and just switches off at all other points. If we take another point corresponding to that point, I have another function which lights on at that point and switches off at other points. Now suppose I take now the collection of all these functions. Now for every omega I have a function, different omegas give different functions because they light up at different points. So f omega 1 not equal to omega 2 implies f omega 1 not equal to f omega 2. So there are as many functions as there are points in the set omega, but the omega is uncountable and therefore this must also be an uncountable. So the cardinality of S is the same as the cardinality of omega, therefore S is uncountable. First thing, is it an orthonormal set? Well, we have to make sure that any two functions are orthogonal. So if for omega 1 not equal to omega 2, what is the support of f omega 1 intersection support of s omega 2? Empty, because this f omega 1 has support at omega 1, f omega 2 has support at omega 2, these two are different, so the intersection will be empty, and therefore integral f omega 1 intersection s omega 2 f g bar f omega 1 f omega 2 bar d mu is 0, because they have different supports, the empty, and therefore f omega 1 inner product f omega 2 is 0. So any two of them are orthogonal to each other, any two functions are orthogonal to each other. What about the length? Only one point, value is 1, so sum of squares is going to be 1. So clearly f omega comma f omega equal to 1 for every omega. So therefore this is an uncountable orthonormal set. So S is an uncountable orthonormal set. So therefore we may encounter a finite orthonormal set, a countably infinite orthonormal set, or even perhaps an uncountably infinite orthonormal set. So we must be prepared to handle all of them. Okay. So we will go through these step by step. So we will first look at finite orthonormal sets. That will tell us how to handle countably infinite, and that will later tell us how to handle uncountably infinite. So we are going to begin with a finite orthonormal sets. Okay, so finite orthonormal sets. So let's take again an inner product space, and S equal to phi 1, phi 2, phi n, a finite orthonormal set. I will do a few calculations with this which are crucial, simple but very crucial. Very simple calculations but very important calculations. I will put them in a little bit probably in a language which in linear algebra also we do sometimes. Now I have n vectors. I can always take the subspace spanned by this n vectors, which is the set of all linear combinations of these vectors. That will give me an n dimensional subspace of the whole space. Okay, so let LS be the subspace spanned by these n vectors in S. So what is LS? LS is the set of the set of all linear combinations of S vectors. Now clearly phi 1, phi 2, phi n is an orthonormal basis for this subspace, because they are all there, they are orthonormal, and every vector is a linear combination of this, and therefore it forms an clearly S is an orthonormal basis for this subspace. Okay. We will do a small approximation problem. We will do a little generalization somewhat later. Right now we need only this. Okay. So this is my subspace LS, and this is the big space. I should not draw above that. That is the big space X. Inside that big space, say, is sitting this subspace. Now, suppose I have information only about that subspace. Then, about any vector in that subspace, I can get exact information because it is already in there. But suppose a vector is outside, then I want to find who is his closest relative in LS, and I can get only that much information. What does that mean? So given an X, in X, want to find vector, let us call it a vector S, of course this will depend on x, a vector Sx in Ls. Let me first make that problem which approximates x with least error. We do not know whether it is possible or not. We want to. Whether we will succeed or not, we do not know. And we will see, we will succeed in a very nice manner. Now, if x is in a already there, then clearly we can take Sx to be equal to x and the error will be 0. Can't be doing anything better than that because x and Sx coincide. The question therefore is when x is outside Ls. So, suppose x is not in Ls. Then what does this statement mean? We want Sx belonging to Ls such that what is the error? The error is the difference between x and Sx and it is quantified through its norm. The norm of x minus Sx, it must be minimum. What does that mean? If I take any other vector and I calculate the error, that must be small for every s in Ls, s not equal to Sx. If you take any other vector, the error will be more. So, Sx should be the best possible approximation of the vector x from among the vectors in Ls. Now, whether it can be done or not, we do not know. Okay, we are going to optimize the error. Most of the optimization problems are eventually brought to some such thing, minimizing some error. Okay, so let us see whether we can do it. What we do is, we do not know where is that, we do not even know whether that Sx is there, and even if it is there, we do not know where it is. So, what we will do is, we will take anybody from Ls and calculate what is the error and see when to minimize that, how to minimize that. So, let S be any vector in Ls. Yeah. The moment I am in S, I am in Ls, I am in great shape because I know a basis for Ls. The moment I have a basis, I can expand the vector in terms of the basis. And since the basis I have chosen is an orthonormal basis, the expansion is very easy. Okay. So, S can be expanded in terms of the orthonormal basis S as what is expansion? You just take the components along the j directions multiplied by the j vector, j equal to 1 to n. That is the standard orthonormal basis expansion. Any x dot I times I plus x dot j times j plus x dot k times k. This is what we do in 3-dimensional ijk vector basis. Instead of ijk, I have phi 1, phi 2, phi n. Instead of dot, I have the inner product. So, you do the orthonormal expansion. So, we have this. So, what are we trying to find? We want to find a suitable coefficient here which will make that error less. So, for we have x minus s, let us calculate the error for any vector s. So, therefore, for any s in Ls, the error norm x minus s we will calculate the square error, because the square of the norm is always inner product with itself. It is easy to write. So, that will be equal to the inner product of x minus s with itself. Okay. Now, I know what is s. I will write the expansion for s. This is x minus summation s phi j j equal to 1 to n, comma x minus summation j equal to 1 to n s phi j phi j, that inner product. Now, again inner product is distributive, I can take term by term. So, first of all I will take x comma x, I will get length of x square. Then this big sum inner product with x, so taken term by term, this is a number, so it will give phi j x. So, minus j equal to 1 to n s phi j x. So, this into this over, this into this is over. Next this into that, again that summation problem, j equal to 1 to n, this is a this is in the second factor. So, how will it come out? With a conjugate s phi j bar and then the inner product of x and phi j. And then lastly this and this, all the cross terms will go away because phi j's are orthonormal. So, only the diagonal terms will come. So, it will be plus j equal to 1 to n x s phi j, again s phi j bar. So, it will be modulus of, I will write it like that only, s phi j bar. So, that is the full expansion. A plus b into a plus b is a squared plus b, it is a minus b into a minus b is a squared minus ba minus ab plus b squared. That formula is what I have written, but these are big terms. Okay. Now, I will write this as norm x squared. Observe, this is precisely the conjugate of this s phi j bar, phi j x, its conjugate is x phi j. So, these are conjugate terms and this is itself. So, what I am going to do is I am going to now do a trick. Not trick, I am just grouping a term. Suppose I write this x phi j minus s phi j into x phi j minus s phi j bar. What will I get? X phi j bar, that is not appearing anywhere. So, that is an extra term, I will subtract it out, which is mod x phi j squared. Then I have got x phi j s phi j bar, that is here, s phi j x phi j bar, that is there, s phi j bar, that is also there. All other terms are there. So, that is just a grouping of that term by supplying, so that I can write it as a product of something with its own conjugate. Okay. So, which is finally equal to, what is that equal to? Norm x squared minus summation j equal to 1 to n x phi j minus s phi j in modulus squared, because that thing multiplied by its conjugate, is it minus plus, then minus summation j equal to 1 to n mod x phi j squared. So, this is the error square for any vector. What if we calculate, take a vector s, I will calculate the error. Let me call this as a error taking s as the approximation for x. Okay. error for x if you take s as the approximation. So, this is the error. What is our aim? We want to minimize this error. Now, that means I must minimize the right hand side. I want to make the right hand side as small as possible. Well, the vector x is given, so I can't do anything with this term, and the orthonormal basis is given, so I can't do anything with this term. So, the only hope for me to minimize is with the middle term, and the middle term is sum of squares, and the lowest it can reach is 0, and that is when each term is 0, and that is when s phi j is equal to x phi j. Okay. So, exs is equal to all this. Okay. On the RHS, given x and s, first and third terms are fixed. And therefore, exs is minimum when second term is 0, that is when s phi j is equal to x phi j for 1 less than equal to j less than equal to 0. Therefore, the required least approximation Sx is obtained by taking s phi j to be x phi j. So, how do I pick that vector that approximates it? Here is x, here is Ls, my x is given. So, what I do is I calculate x dot phi 1, x dot phi 2, x dot phi n. I got n numbers, use those n numbers as the coefficients and construct a vector x dot phi 1 phi 1, x dot phi 2 phi 2, which is going to be here. So, that Sx will be here, because it is a linear combination of phi 1 phi 2 phi. So, that is the best approximation. We get a clear cut answer. You give me the x, give me the phi, I know exactly how to construct that Sx. Simply calculate the inner product of this vector with the given orthonormal vectors and construct the linear combination. You will get a vector in Ls, and that will have the least error. Okay, so this is the first least square approximation problem. This is essentially what all least square approximations are about. Okay. Okay, so that's the first result. So, result 1, let S equal to phi 1, phi 2, phi n be a finite orthonormal set in an inner product space, and Ls the subspace spanned by S for any x in x, define Sx to be equal to summation j equal to 1 to n x phi j phi j. Then Sx belongs to Ls, and norm of x minus Sx is strictly less than norm of x minus S for every S in Ls, S not equal to Sx. For any others, the error will be more. That is the first approximation problem we have got. Okay. Now, I will reel out a few consequences out of it, which we will use in the next class. Okay. Some consequences of our calculations. Okay. Where was I? Okay. Look at this calculation. what is the least error? This is EXS. The least error will come when I put S is equal to Sx. When I put S is equal to Sx, this term disappears. The least error is norm x squared minus this. Okay. And the least error and norm of x minus Sx squared is equal to norm x squared minus summation j equal to 1 to n. What was that term? Norm x phi j squared. Okay. That was the least error, that is the least error I can get by making the middle term as 0. Alright. Now look at this. This is the norm square. So therefore it has to be either 0 or greater than 0. The norm can never be 0 and never be negative. So this is non-negative and therefore this has to be non-negative. So first consequence, from 1 we get 0 is less than or equal to norm x minus Sx squared, which is equal to norm x squared minus summation j equal to 1 to n x phi j squared, which implies if I bring this to this side, j equal to 1 to n x phi j squared is less than or equal to norm x squared. This is the generic Bessel's inequality. Okay, this is the starting point of, in a more general way, form of the Bessel's inequality. But this is the Bessel's inequality for finite. So what does this say finally? If you had any finite number of orthonormal vectors, phi 1, phi 2, phi n, whatever be the n, as long as you have a finite number of orthonormal vectors, if you take the components of any vector along these orthonormal sides, the sum of the squares cannot exceed the norm of the original vector. So that is consequence 1. And you will see slowly that we are connecting to somewhat similar to what we did with that L2 omega soon. Okay, consequence 1. Hence consequence 1. For if S is equal to phi 1, phi 2, phi n is any finite orthonormal set, then summation mod x phi j squared j equal to 1 to n is less than or equal to norm x squared for every x in X. Okay, that's a first important consequence for us. So now let us look at the second consequence. At least let me complete that and then I will see, move to the real L2 connections later. Let us look at the second. Now suppose I move to the next stage. Instead of a finite orthonormal set, I have a sequence of orthonormal vectors. So let S be phi 1, phi 2 be an orthonormal, be an infinite orthonormal sequence. So I am now know something about finite orthonormal sets. I get a little bit bold and start going to the next stage. I have a sequence. Then for any n, look at Sn equal to phi 1, phi 2, phi n, truncate it at n. That is a finite orthonormal set and therefore I can apply consequence 1. is a finite orthonormal set, and therefore by consequence 1 we have summation j equal to 1 to n mod x phi j squared is less than or equal to norm x squared for every x in x and for every n. For every n I can do that. N equal to 1 it is true, n equal to 2 it is true. Then what does that tell? This is a series of partial sum of a series, infinite series, and as I go on increasing n, I get the sums getting bigger and bigger. So the partial sums are non-decreasing sequence, they are bounded above by norm x squared, and therefore that must converge. Okay. So therefore limit intending to infinity summation n j equal to 1 to infinity mod x phi j squared exists and is less than or equal to norm x squared. But what is the limit? That is exactly what is the sum of the series. So that is the consequence 2. So the consequence 2 is so consequence 2, if S equal to phi 1, phi 2, phi etc. is an infinite orthonormal sequence in an inner product space x, then summation j equal to 1 to infinity x phi j squared is less than or equal to norm x squared for every x in x. And this is called Bessel's inequality. This is the famous Bessel's inequality. In any inner product space, for any infinite orthonormal sequence, the sum of the component squares along this direction for any vector cannot exceed the norm of the vector square. Okay. This is all intuitively okay, but now we have completely justified it. Of course, in the finite case is we already have. It is from the finite case only we went to the infinite sequence case. Okay. So this Bessel's inequality is one of the most fundamental inequalities. Okay. It essentially tells you about errors. There are many questions that we will ask. When will this become equal? Okay. Suppose we want it to be not less than or equal to, when will equality take place? Okay. It turns out that equality will take place, then suppose the equality takes place, x phi j squared is equal to norm x squared, okay, and that is called the Parseval's identity. Okay. That equality when it takes for every x is called the Parseval's identity. Suppose equality takes place, then there is this optimality property of the orthonormal set, that is ultimate in size. You can't expand it any bigger, which means it is a maximal orthonormal set, and that is called an orthonormal basis. Conversely, if the set is an orthonormal basis, equality will take place, and in that case every vector x can be expanded in terms of the sequence as a x comma phi j, sum is equal to j equal to 1 to infinity, and that is called the Fourier series of the vector x with respect to the orthonormal basis. Fourier did it for a special case. He took the inner product space to be 2 pi periodic functions with the inner product as integral f(x, gx bar dx over 0 to 2 pi or minus pi, and then he took a special orthonormal sequence 1 over root 2 pi e to the I n t, and then he did all this. It is an orthonormal basis. He claimed all this. He said, I can expand, that's all. He never gave a proof. But he was properly admonished by his the people who selected him for the award of the French Academy, which included Laplace and Legendre and people like that. They said, it's all right, you have got a very good idea, but it is completely lacking mathematical rigor. However, they gave the award for the sake of the idea that he came up with, and subsequently 150 years of mathematics, step by step justified analysis, everything that he did can be interpreted properly. And then that got generalized, and now we talk about Fourier series in an abstract Hilbert space with respect to abstract orthonormal sets. Okay, and that's what I will do next. I remember when I was in BSc, we had I tell this always, we had a Shakespeare unabridged called Hamlet. I don't know whether you have read it. In Hamlet, we were taught by one Father Colasso was my English professor. This man would walk into the class with so many books and then keep it on the table. And then one scene in Hamlet, then he would say, Bradley says, and then I read about, there's a famous critic of Shakespeare by name Bradley. And then you go on reading Bradley, what he says about this particular scene, but that particular dialogue and things like that. And once there was an exam, there was some critical essay we had to write. I concluded that lecture, for which I got admonished by the teacher. I wrote that, however, if Shakespeare comes back alive and takes an exam in Hamlet, he will fail if he doesn't read Bradley's criticism. Okay. So today probably if Fourier comes and takes an exam on Fourier series, he may not even understand what question they are asking. It has been so generalized and so abstracted. But what we will see is only in the context of Hilbert spaces in general, and we look at various examples. Okay. So the next topic will be to look at when Bessel's inequality becomes equality, how it leads to the notion of orthonormal basis and Fourier series. Okay. I think it's time to stop.